These are notes for section 7.1 and 7.2. 7.1 is just three definitions. You'll get those in your reading questions. Please make sure you know the difference between a random variable and an algebraic variable. Very quickly, one of the important distinctions is in an algebraic variable, you can plug in anything for x. It doesn't matter. You can plug in negative numbers, you can plug in positive numbers, you can plug in decimals, etc. Random variables we show with a capital letter, and a lot of times they follow rules. For example, something could be normally distributed with a mean of 4 and a standard deviation of 1. So again, big difference is random variables follow rules and we label them with capital letters. Today's lesson, it covers discrete random variables, and then the next lesson will cover continuous random variables. So discrete random variables, their information is conveyed one of three ways: either in a table, in a diagram, most often a histogram, or sometimes you calculate them using a formula. And a lot of times you'll be using multiple versions of all these. So for example, this formula you'll learn later in the chapter, this is how these numbers are calculated. All these probabilities are calculated using that formula there. We're not going to use the formula yet. Today I'll give you the numbers that you need. So if x represents the number of heads in 4 flips of a coin, you're bound by 0 and 4. If you flip a coin 4 times, you could get 0 heads, or 1, or 2, or 3, or 4 heads. Taking those probabilities and displaying them graphically, here's a histogram. And just like we did much earlier in the course, you could describe that histogram with the center, shape, spread, and unusuals. Okay. Now we're going to focus in on the y values of the numbers of the probabilities to answer questions. So question 1, use the table to find the probability that x is less than or equal to 2. That's saying, what are the chances that I get 2 or fewer heads in 4 flips of a coin? Well, it's not that hard to look at the table and see that I need these 3 numbers. The notation is if x is going to be less than or equal to 2, that means x can equal 2, or 1, or 0. Grabbing those probabilities off the table, adding them together, you get that. The probability that you get 2 or fewer heads in 4 flips of a coin is 0.6875. So the second example, translate the probability of x greater than or equal to 3 into words and then calculate. X greater than or equal to 3 means you're going to get 3 or more heads in 4 flips of a coin. Going to the table, x greater than or equal to 3 means I need the probability x equals 3 plus the probability x equals 4. Add those together, you get 0.3125. Okay. For this section, you might have to create the distribution yourself, which is going to be a little bit of work. So 30 averages for birth genders produced. Boys are slightly more likely to be born than girls. So the probability of a boy is 0.5126 and the probability of a girl is 0.4874. Those are real numbers. I didn't make those up. So in a 3-child family, what are the chances that you get a ordering of girl, girl, boy? Well, since births are independent, in other words, the gender of one girl the gender of one child doesn't affect the gender of the next. Girl and boy can just be multiplied. Probability girl times probability girl times probability boy, in which case you get 0.4874 times 0.4874 times 0.5126 for 1218. What about the probability of girl, boy, girl? Well, girl and boy and girl, since multiplication is commutative, in other words, order doesn't matter, it's going to be the same 3 numbers, 0.4874 squared times 0.5126, and you still get 0.1218. So now if we need the distribution for this situation, if we're going to have 3 children in our family, and if we want the probability distribution, the possible outcomes are 0 girls, 1 girl, 2 girls, or 3 girls. I'm going to list all the different orderings. If I'm going to have 0 girls, the only way of getting that is a boy, boy, boy distribution. If there's going to be 1 girl, that girl can be the oldest, or the middle child, or the youngest. So there's 3 different ways of getting that ordering, and we'll calculate the probabilities in a second. For 2 girls in the family, girl, girl, boy, boy, girl, boy, girl, girl is the only way of ordering. And if there's going to be 3 girls in the family, there's only one way of arranging that, which is girl, girl, girl. So the first thing we did is we found the number of arrangements. 1, 3, 3, 1. Second thing we need to do is find the probabilities. What's the probability if you get a boy and a boy and a boy? Well, again, because of independence, probability of boy is 0.5126. If it's going to be boy times boy times boy, just cube that and you get 1374. For the 3 different ways of arranging 2 boys and a girl, The boy probability is squared. The girl probability is just 1 time. Multiplying those probabilities times 3, because there's 3 possible ways that could happen, 0.3842. Going in a similar manner, 3 ways with 2 girls and a boy. 3 times probability of boy times probability of girl squared produces this. And then finally, girl, girl, girl. Only one way of arranging that. Probability of girl is there. Cubed, and you get that. Putting these into a table that summarizes it, the probability that capital X equals lowercase x, probability of number of girls in a 3-child family is 0, 1, 2, or 3, has those 4 probabilities there. So the last problem you're going to finish on your own, the probability of at least one boy. Well, we were given a distribution for girls, so now you've got to change at least one boy into a statement about the number of girls. So at least one boy becomes a probability of what in terms of girls. Write that using an equality notation and then get your numbers and the answer from the table above. So do that on your own and we'll be checking it in class. Okay, that's it for the first video.